Welcome to Brain Vision.
Given the wave functions, including the mixed state wave function, we're going to start with the ground state, and we're going to take the expectation value for the position operator. And proceeding, we get the following integral. And we see that this is going to be an integral over an even or symmetric interval, meaning that it's symmetric about the vertical axis, the y-axis. In other words, it's an even interval or symmetric interval about the origin from minus infinity to infinity, but this is an integral of an odd function. So from that observation, we can already conclude that this integral should be 0. You could also look this up in an integral table, or real quick, you can actually do the integral by making a quick change of variables, as I'll show you. So there's a real quick way to do that. You can write this as two integrals. So an integral from minus infinity to 0 and an integral from 0 to infinity, and you'll perform a change of variables on just the first integral. So we basically change x to minus x. That's the change of variables. And when we do that, we get an integral from infinity to 0. We leave the second integral alone, and this is the form that we now have. So in doing that, we come to this next form. We flip the integral on the first integral itself, and we have a minus sign. Now notice that the minus sign on negative x right here has canceled with the minus sign in d negative x. And the minus sign in negative x up here has gone away because it's negative x squared. So that leaves us with x dx in the next line, and we just have e to the negative ax squared. So we just have a minus sign right here simply because we flipped this integral right here. So now this integral will cancel with the integral that we left alone on the right, and we therefore have 0. So the expectation value for x in the ground state is 0. Next, we continue and we calculate the expectation value for x in the first excited state. But again, we have the integral of an odd function over a symmetric interval, and we get a similar result. We should get 0, but we go ahead and just write out this same trick, this same procedure right here, and it works the same way except that it's x cubed. Had this been an even function, then because you're squaring or taking to the fourth power, etc., this method would not work, and you would not have integrals that cancel out. But if you have 1, 3, 5, etc., for odd functions, they do cancel. And so you see once again that these integrals will vanish because they add together. The minus sign causes them to cancel. So now we finally come to the expectation value for x in the mixed state, and we get 3 terms. When you substitute in the mixed state in the expectation value formula, you get an expansion, and there are 3 terms that result in that expansion, and one of them is a cross term, which gives us this 2 in the cross term, and the other 2 are square terms. The square terms will look familiar. We just calculated them. And notice that we have the 2 there in the cross term because you had 4 terms since it was an expansion, so they should add together to give you the 2. We just calculated the square terms. They vanished. So this leaves us with just what's left over, 2 times the cross terms. But the 2 with the 1/2 are going to cancel. And so now we just have that our expectation value equals the integral of x times the 2 wave functions. And the only reason I have absolute value signs is in case we were dealing with complex valued functions. And I like to be general and just include what goes into a formula in its most general form. But we don't really need them because we're dealing with real valued functions. So when you substitute everything in for these particular wave functions, this is what you obtain. And it looks like this. Now notice we finally have an even function over a symmetric interval. And you could evaluate this using particular methods. You could research Gaussian integrals, for example, and see how they're evaluated. You can just look in a table of integrals, which is what a lot of people do. And because we don't have a lot of time, we're just going to state what this integral is equal to. So when you look it up in a table, for example, or if you do like to just see how it's done, you could look it up. You can use polar coordinates to evaluate this type of integral. This is what you get. And so there's some cancellation that'll go on when you have all these numerical, or basically all these factors multiplying each other, and you finally get 1 divided by the square root of